In lesson 9.1, we are going to continue looking at the end behavior, so end behavior part 2 of polynomial functions. So if you have not had a chance to look at 2.8, please make sure you've watched all those videos for 2.8 before we move on to 2.9. In 9.1, they want us to match each of the graphs of the polynomials with the equation it represents. So one of the things that we want to remember from 2.8 is that if the end behavior go in the same direction, then they have to be an even degree polynomial. So if you have an even degree, then the end behaviors go in the same direction. So I'll go ahead and write even degree, same direction. And if you have an odd degree polynomial, then we're going to go in opposite directions. And of course, we're talking about the end behavior here. So before we even look at the equations, why don't we go ahead and agree out of A through D if we have an even degree or an odd degree. So on A, the ends are going in the same direction. They're both heading up. So this has to be an even degree. They're doing the same thing. Now on B, it's a little bit weird. This is just a flat line, and the ends are doing the same thing. So because the ends are doing the same thing, this has to be an even degree. And the fact that this is a flat line, I know that the function has to be a line. When I look at C, over here on the left, you're going up, and over here on the bottom, you're going down, or on the right side, you're going down. So this has to be an odd degree. And on D, we got the same situation where they're going in opposite directions, but in this case, it's just kind of flipped from part C. So this is going to be an odd degree. So now that we know at least who's an even degree and who's an odd degree, let's go ahead and look at the equations. So on number 1, my equation is not in standard form. It's actually in factored form, so I don't quite know the degree of the polynomial yet, but from, I think it was like lesson 2.5 or 2.6 or 2.7, one of them, you know a quick way to get the degrees by multiplying all of the variables. So I'm going to multiply this outside x times this inside x times that x, which is a negative x. And when I multiply this, I'm going to get a negative x to the third. So I know that this is a degree equal to 3. And it's got a leading coefficient equal to -1. Number 2 is pretty easy. Number 2's got the polynomial in standard form. So I automatically know that my degree is equal to 4, and my leading coefficient is a positive 5. Number 3, the function is it's not in factored form really, and it's not in standard form yet because there's still some math to do. So I'm going to distribute the 5. I'm going to get 5x plus 15, carry down that minus 5x. And when I go to combine my like terms, this 5x and that negative 5x cancel with each other. So this leads me to y equals 15. Now this does have a degree. Every polynomial does have a degree. And in this case, because you're missing the x, your degree is 0. And your leading coefficient is also 0. So let's go ahead and use this knowledge to help us match up the graphs. I know that number 3 is a flat line, right? This is a constant function because there's no slope to it, right? There's no 3x or 4x to it. It's a constant function, which means it's a flat line. There's no rate of change here, so it's a flat line. And if you look up at our choices, choice B is the only one with a flat line. So we are going to go ahead and match B with our function. Oh, you know what I just noticed, guys? That's the axis. There's my function. So I was wondering why that looks kind of funny. That's the actual function right there. All right, let's look at 1 and 2. So I definitely know that the graph for number 2 has to go with A because it's an even degree, right? And A is the only other even degree that I haven't matched up. So we are going to go ahead and I'll color code it. Number 2 is going to go with choice A. So that leaves number 1, which is an odd degree polynomial. It's either got to be C or D. So we kind of have to reason this out a little bit to figure out which one could it possibly be. So I think I'm going to use some input values to help me figure out which one it could be. So if I were to plug in some positive x value, let's go ahead and I'm going to pick my favorite number, which is 5. So I'm going to go ahead and test out x is equal to 5. If I put 5 into this polynomial, so it's going to be y equals 5 times 5 plus 3 times 2 minus 5. Let's see what kind of output we get. 5, 6, 7, 8, negative 3. And you know what? I don't even care really what that is. 5 times 3 is 15. I don't even really care because the whole point is that my output's going to be negative. So I know over here on graph D that if I put 5 into there that you're probably going to get you need an output of a positive because if you'll notice as you keep getting bigger and bigger with x, they're all getting higher and higher. But on graph C, if I keep getting bigger with x, my outputs are down here in the negative region. I'll even highlight that. Your outputs are in the negative region while the outputs for positive x's are in the positive region. So I know that choice C must be my graph. And I want to pick out a different color. Let's do orange. Orange is fun. Choice C has to be my graph for number 1. So here's just 2 strategies to kind of guess your way through a graph and its related function. First, see if you can identify or match up based on the end behavior, whether it's an even degree or an odd degree. And then, if you still have to keep choosing, test out some input values to see whether your outputs are up in the positive region or maybe if your outputs are down in the negative region.